I think we are live. So please, you can start, Min.
Yeah. Okay. So thank you, Jem, for scheduling the talk for me. So hello everyone. My name is Min Si. I'm a computer scientist from Argonne National Laboratory, and my work involves in the high performance computing in a smaller scope. It's more related to the communication subsystems that we are doing for the high performance computing systems. So it's my great opportunity to attend the rebase talk today and be able to discuss with everyone regarding the challenges, opportunities we found in the core design for high performance computing software systems. And let's get started here. Yeah, so so I think not everyone in this room has very familiar with the HPC community because it's a relatively small community in computer science. So let me recap about the community a little bit to everyone. So we have HPC we have HPC basically, they are traditionally designed for the scientific computing applications. So that's why their customers is just a small group. And the goal of the HPC system design is to provide extreme scale parallelism and extreme powerful computational power, because the computation requirements in the scientific applications are truly intensive. That those cannot be done on your PC laptop, of course. They cannot be done efficiently on cloud, for example. So that's why we design those special hardware for that. And the system, as we just said, they are traditionally designed for the very computational expensive simulations. But in recent years, because we are seeing a lot of interest in doing data intensive analysis on this supercomputer for scientific discovery, and as well as industry innovation. So the new trend of the supercomputers are also optimized for the data intensive access. So in these slides, I basically copy pasted some fancy pictures that demonstrates what we are actually doing on those machines. So at the bottom, you can see that will be the Aura supercomputer. It will be public to everyone at late next year at Argonne. And on such kind of supercomputer, which kind of a house size machine, we are doing a lot of simulations. So for the pictures, you can see there are molecular simulation, there are genome analyze, there are also simulation for the fluid physics simulations. So and we found this extreme computational power can help many domains in scientific discovery as well as industry, for example, like manufacturing, like the aircraft design, and so on. All right. So given such powerful system, working on the software of it is not easy. It's actually very challenging. That because of several reasons. So if we are looking at the trend of the HPC architecture innovation, we can find that we are getting more and more complex software because of the requirements for applications. We are also getting the hardware more and more complex. So for the software, as we have seen in the examples in the previous slides, we are seeing there are simulation requirements as well as the data analyze deep learning requirements recently. That's why essentially adding more complexity in software. In the hardware side, as everyone knows, that's end of Moore's law. It's not a new sentence, everyone knows that. And so if we can see the very early version of the supercomputers, maybe in the tera scale, if you can see there in the very beginning of the trend, they are basically just the Intel Xeon CPUs. But of course, we cannot increase the single core frequency anymore at that time. So we are seeing we are increasing number of cores gradually from petascale to 10 petascale to 100 petascale. Okay, now when we hit in the 100 petascale, for example, the Tianhe 2, it's about 30 petascale, of course, and the Summit is beyond 100 petascale. Those systems, we found that the core parallelism will also be insufficient. Why? Because we are considering not only the power, but also power per watt. So they are trying to change the processor architecture to make it more efficient for energy consumption and getting the same level or higher level of computation power. But eventually getting the system more and more complex. So for example, as I show at the end of this trend, of course, that's not in real case, but Aurora, which will be for next year, it will combine Intel CPU, Intel GPU, and for the memory system, it have a high bandwidth memory, DRAM, and a persistent memory, and storage, and so on. All right. So on those kind of complex architecture, now we are designing a software stack for it. As I can see that the software stack on HPC is one of the most deep and wide, deepest and widest system in the computer science community. So in this picture, I just show a subset of it. It doesn't mean that's all. So we just show some typical internal components of the software stack. So for example, we have the different computational requirements from different applications, for example, from the traditional scientific simulation, as well as from recent emerging TensorFlow, Python, the PyTorch, those kind of deep learning frameworks. So if we consider the actual computational requirements from computer science point of view, there are many differences. For example, some of them are compute bound, some of them are memory bound, but some of them are IO bound. So I have to design and optimize different components of the subsystem to address the performance limitation of all of those application patterns. From parallelism-wise, we have both traditional box synchronization parallelism as well as some irregular data-driven parallelism. So the communication system becomes complex too. Of course, from application level point of view, we have the simulation as well as training, and also some inferences also happening on the supercomputer machines now. So those adds all the complexity that we have to address in the software stack that make it very fat. On the other hand, we have so many different hardware in the supercomputer now. So for example, if you can see, we have the off-node communication libraries that are address the data transfer across interconnects. And now since we have CPU plus GPU, in near future, I know some actually supercomputer already have FPGA in their system. So we will have both the thread system that's running on CPU and well as the accelerator libraries designed for the accelerators. For I/O is complex too, because we are trying to parallelize the data load store and on different file systems. So all of those differences and the different components in software stack will be finally compiled and combined into a single execution file, maybe several library files, but it's a single binary and running on the supercomputer. All right. So our work is to design and develop this kind of software stack. It's a real challenge in both development and design as well as performance. Of course, we are working very hard to address the design and development challenges. So through the next few slides, I would like to share what we actually see also from the performance challenges through two showcases that actually relies on such deep and wide HPC stack. All right. So the first application is NWChem, which is a very widely used high-performance computational chemistry application. It's mainly designed for the quantum-level simulation of molecular systems. It's so expensive in computation and also in data movement across computing nodes. So now we are using it mostly only for small systems. We are going to the next generation of supercomputers like exascale, post-exascale. Of course, we're expecting that we can use those highly precise quantum-level simulation also for large systems, but that will be in your future. Okay, and it gives you so many simulation capabilities in the software stack. It gives you molecular electronic structure and so on. And if we just check the lines of code, the code itself is big too. It's about 4 million lines of code. And the total investment for it is actually more than 1 billion today, but actually the data 1 billion number is actually a little bit outdated. So they are actually doubled in recent years, because I know the NWChem team, they are adapting their application, basically means full rewriting of their application code to adapt it to the exascale supercomputers. So that's a very expensive development cost, and it's a highly optimized system. So if we decouple the application stack for NWChem, we can see that it actually has several layers combined for the software part. This allows us to relatively simplify the code logic of the complex application. So for example, for the data movement path of the application, we can see it has a global arrays layer, and later in the bottom of global array, we have an ARMC layer, and then we have ARMC MPI, and so on. So each layer of the software stack is handles a different level of abstraction. So for example, the global arrays will provide the application developer a abstracted distributed array. So basically, the application developer will not consider how I distribute such a huge matrix that I will use in my application onto different computer nodes. They will just say, okay, that's a huge global array. And then the global array runtime system will internally distribute such big array into different computing nodes physically. So that's a major role of the global arrays. And so RMC MPI, it defines the communication interface for global arrays, because as we see, the array is distributed across different nodes. We definitely need to move data between each node. So the RMC layer will provide such capability. And RMC internally have different implementation. We create a port for different hardware, for basically for different network. For example, they have the InfiniBand port, which is designed for InfiniBand system. They have DMAP port, which is designed for the Cray supercomputers. And we also have the RMC MPI port, which based on the assumption that we port it on portable MPI implementation, because MPI is more widely used on many HPC systems. So we assume it's a portable network support. Okay, so that's how the deep HPC stack for NWChem looks like. All right, so now we are moving to the performance aspect of the NWChem. So NWChem really performs a very like a typical computational pattern called get compute update. Most of the computation involved in NWChem is matrix multiplication, but the matrix is very big. And the matrix is actually a multi-dimensional tensors in NWChem. So in this picture, we just show 2D matrix for simplicity, but you can consider it's a multi-dimensional, like 7-dimensional tensors in some tasks in NWChem too. So what they do is that they distribute such huge matrix into different computer nodes, in global, for example, in global arrays. And then when each process process the task, they will get a subset of the matrix into its local memory, and then do a degen computation on its local memory, and then update its result back to the remote global array. And we see this software stack, it looks like they get and update communication requests goes from NWChem down to all the way down to the OFI. So that's how we handle the data movement in the deep stack, okay? So, but if we really look at the performance itself, it's really inefficient, I would say. So there are several drawbacks we have already observed. One is that the low-level communication subsystem like MPI, like OFI, they don't expect their implementation feature to the application layer. So one example is the application layer assumes that I can issue the one-sided communication. We also call it an RMA communication that can be natively handled by all network hardware. But that's not true. On most hardware today, for the network part, we still have to emulate the one-sided communication in software. But that's not noticed by the application side. So they basically just write, I do compute, and then I do some communication, like in the get compute update model. And then what we observed is that in some extreme computation expensive tasks, like CCSDT, which is a very important task in NWChem, we can see up to 15% of the time are concerned by the RMA part, which means for that 15% of time, all of those the computing cores are basically idle and waiting for the network data transfer completed. That's an extremely inefficient performance. And if we can see the root cause of such efficiency, it's really just because the low-level communication subsystem, let's say MPI RMA over OFI, cannot handle the complex one-sided communication in hardware. So they assumes that I need a remote process to progress my communication. But if the remote process is working for some heavy computation like DGEM, then it actually causes the delay in communication. That's why we have seen such heavy overhead. Okay, another example of the performance inefficiency is regarding the computation and the communication resource management. For example, when we consider, okay, now I need to give some, since the communication are emulated in software, so now I need to give some computing resource like CPU cores to progress the communication. But how many cores I need to assign to communication and how many I need to assign to computation? That really depends on the computational pattern in application. So, but in the NWChem such kind of complex application, we see that some of their phases involves redundant data movement, but some others are on the other side. For example, they rarely issued communication and money spent time in computation. So for the runtime aspect of view, they cannot detect which is the best configuration to do the resource assignment for computation and communications. Okay, so the graph just shows we get very suboptimal performance. There's no way we can get the best performance for all internal phase by using a single static resource configuration. That's what we can see for the NWChem deep stack. Okay, of course, I will share some experiences about how to address those challenges in the later slides. But let me go to another example, so I think the audience can know what actually challenges we have from different applications. The second example I would give is QMCPACK. This actually shows how wide the HPC stack can be. The HQMCPACK is a quantum Monte Carlo simulation for material science, mainly used for material science, but now it's being used for other scientific domains too, because the physics models are basically portably used for different problems. They provide many capabilities in the software stack, and they have the variational Monte Carlo, diffusing Monte Carlo, and then so on. And the pictures I passed here basically are simulated by the QMCPACK software package. All right, so let's quickly move to the software stack for the QMCPACK, as we are not trying to understand the physics meaning of QMCPACK. Okay, so what QMCPACK needs to resolve from computer science point of view is that they have the physical system is very large and bound by the memory capacity. Because their implementation involves a large replicated in symbol table that actually can be gigabyte size and more. And it depends on, of course, depends on the input, the material properties. But if we consider we need each process to handle such kind of huge replicated symbol data, it's basically impractical to run on most HPC systems. So the QMCPACK team decided to do a hybrid approach to parallelize the code. They use MPI plus OpenMP, and recently added CUDA support to leverage the GPU. So the benefit for the MPI plus OpenMP hybrid programming is that it can share the large ensemble table among different processes on a single node. So if you can see in this picture, we have two MPI processes. They may run on two different compute nodes. And to leverage all the cores on each single node, they create many number of threads. So those threads can share this huge replicated incidental data. And of course, they will exchange data at each iteration across processors. That's how it looks like. And recently, is also either NVIDIA GPU's acceleration. So the code may slightly become different, but the main pattern does not change. So we can consider the QMCPACK. Basically, it combines the MPI, OpenMP, and CUDA subsystem in their software stack. Okay, so what's funniest we found in this combination is that because of the lack of interoperability between those runtime libraries, we hit a lot of performance bottlenecks. Of course, because I'm working on the MPI project, so of those challenges I show here are basically from our observations in MPI. But I would say these issues is actually a general issue and exists in many other unknown parallelism and offload communication libraries too. Okay, so what we can see from those two challenges, the bottlenecks, one is that still today, most of the HPC applications, they write their MPI plus OpenMP code by following the funneled mode. So what does funneled mode mean? It means they use multiple threads, for example, OpenMP parallel for loop to parallelize their local computation. And then they will allow only a single thread, basically a master thread in OpenMP to issue the communication. And once the communication done, okay, they get back to the parallel for parallelism again for computation. There are some ongoing innovation in task-based model. For example, in OpenMP, they have different performance per time. But now we are just showing the what's a dominant of the applications use. Okay, so what does we find in communication is that since only a master thread is issuing the communication, most of the other cores are basically idle when we are doing network data transfer. Of course, on some many core architecture like Xeon Phi, they also degrade the performance of communication because now we only have a single low frequency core issuing the software instructions for handling the data transfer. So that's basically one bottleneck we have seen in the QMCPACK stack. The other one, there are also another challenge we have seen. So that's basically caused by the MPI implementation limitations. So one would ask, okay, since you have only if we have only single thread issue MPI, I will get the first challenge. No, how about we just use multiple threads issue MPI concurrently? It may address the trouble we have observed, but that's actually very hard to achieve in practice because most of the mainstream implementations, they are not designed for threads. They are designed based on process level. So what you can see in most MPI implementations is that they basically do a global lock to lock all the internal critical sections. Of course, we have the reasons to make the critical section because they cannot be shared concurrently accessed by multiple threads to ensure the semantics correctness of MPI. And then when we get into the low-level network hardware, when we are trying to issue the communication command to the hardware, now we see that although we have so many threads active in the application, only a single thread at a time can hit the hardware, can issue the data out to the network adapter because they are all serialized by the internal critical section. On HPC systems, we usually have the multi-port support for the network part. So basically means you can have multiple cores concurrently issue the data through the network adapters. So they get the all handled by network in parallel. But in this picture, we can see that we actually cannot do that in the application level because they are all serialized by MPI runtime. Okay. So so I just post a few examples of the performance challenges in the deep and wide HPC stack we have observed in the past few years. I have to summarize a little bit that the deep and wide HPC stack is not bad because we are isolating, we are abstracting different component functionalities we need to resolve such a complex computational task. But there are some good aspects, like we simplify the problem, so each layer of the developer can handle their job relatively easily. We can also achieve generalization, component reuse. So for example, we have the communication subsystem, IO subsystem, OpenMP. They can all be used by many different applications. That's all the good aspects. But of course, that there are drawbacks of this deep and wide stack, as we just showed in the previous examples. The lack of information sharing and coordination across different components. That actually causes suboptimal performance. And we are at HPC, we are caring about any performance drawback in principle. And when we are hitting exascale, we know it's very hard to get a full utilization of all computational communication resources. That's why we are even more care about earning performance loss that's caused by the HPC deep and wide stack. So here we give the words core design, and so what we are trying to do today is that we do core design across the different software stack and also between software and hardware. We were trying to minimize those suboptimal performance, suboptimal resource utilizations. Then we can enable the full scale performance in our HPC systems. That's basically what we are trying to do today. So in the next slides, I would like to show what we actually did in the past few years. Of course, they are just early investigation. They are still ongoing, and core design is not an easy work, but we can get insights from those experiences. Okay, so my first showcase would be to address the software emulated communication in the NWChem application. So what we are trying to, we did is to design a communication runtime to support the progress and the communication resource management for the application. That actually requires the application and the communication systems core design. Okay, so through this system, we can see just compare those two different software stack. We add a Casper layer, which manages the communication resource for MPI. So it can make, for example, use additional CPU resource to handle the incoming communication. Thus, they don't need the computing process to process the incoming message. So we don't have the delay caused in the incoming army communication. That's basically what we do there. And actually, it's still software layer communication progress management. But actually, we see the performance of this approach can give us basically similar performance as we can see if the communication is fully handled by network hardware. So this idea is simple, but when we are hitting the multi-phase application, which is basically the true type for most HPC applications, we are hitting problem. So this is still not a perfect solution, I would say. So if we summarize what we did to resolve the software emulation in the previous slides, we are essentially adding more computing resource, CPU resource, basically, to handle the data movement. Because the network hardware, for example, the NIC, the network interface card, they are not powerful enough. They're not able to handle very complex data movement. For example, if data movement is for non-contiguous data, that's complex. And if the data movement involves some computation, that's even more complex. So the NIC today, they actually cannot handle such requirements. So that's why we need a CPU resource to help. So now we are getting into the resource management problem. Since we need to, we need the computing resource CPU for both computation and also for communication, we need to make a balance here. So as a summary, we could assume, okay, if my application is very computation intensive, I would just assign a few number of CPUs to handle the communication, and then I can utilize all the other cores or even GPUs resource to handle my heavy computation on node. If my application is communication heavy, then I would assign more cores for communication, so we don't have the bottleneck for the communication part. But for applications, if they have the multiple phases and some phases are heavy computation and some others are heavy communication, what we can do there? It's very, and so from the software design point of view, it's very hard to dynamically change the number of cores. I mean, it's possible to change the number of cores you assigned for each computation and communication. But the problem here is, from the runtime system point of view, you don't know whether this phase is computation intensive or whether it's communication intensive. So how we can make the right decision? Of course, we addressed such a challenge in our project, but it's not ideal. It's not perfect yet. So here we just share what we have done so far. We studied several different approaches to dynamically manage the CPU resource for computation and communication. We did both application-guided approach. Essentially means we let the application expose the information about how many resource you needed to issue a communication. For example, if the application knows I will be very computational extensive, then I will require more cores for computation rather than communication. We also did a runtime pure automatic and runtime profiling based approach. And so at the runtime, we trying to insert the timers and we do prediction for the need of communication resource for the upcoming phases. Well, both approach actually worked, but we can compare the performance here. The profiling based adaptation is not very, it's not as good as the guided approach. There are several drawbacks that we actually cannot eliminate it. One is that, of course, we added the timer to profile, so there are profiling overhead that cannot be avoided. Second, the prediction takes time. So for example, in our system, we trying to predict the behavior change in the next minute or 2 minutes, but that minute actually, it's very important in the application. So it essentially delays the change or the adaptation of the resource management in the application and causes delay. So we can say the performance, there's still about 10% difference in the two approaches. Okay, so here I also want to show what we can perhaps do better if we can do a larger scope of core design across application and runtime system. So this problem, actually, we cannot resolve it today. So what I want to show here is we found through the adaptation system, we actually observed that the application like NWChem, they are still getting some communication patterns. They are not balanced, distributed across different computing nodes. Basically, we call it bad data locality. And this issue is very hard to be observed by application developers. Believe me that that's already a highly optimized application package, and that they paid a lot of investment for that. But still, they will get this trouble, and it's very complex to actually ensure perfect data locality in application algorithms, because algorithm itself is already complex enough. So as an idea, we probably want to propose in near future is that since the runtime can actually detect such trouble, rather than relying on the human experiments, can we use such information to automatically improve the data locality for applications? So that's basically the information exchange and the coordination across the runtime system and the applications. That's basically an essential goal of the co-design. Okay. So here I just basically summarize what we actually learned from the communication resource management. Okay, so we learned that we need the efficient utilization of HPC resources, and we need to have a full understanding and coordination between multiple software layers It requires us to understand the behavioral application, understand the cost of the low-level communication, as well as the limitation of the hardware. So to make a really efficient application for the upcoming supercomputers, we have to actually cross the boundary of all those layers and make a co-design effort for that. Maybe another effort will be touched into the hardware part. So as I mentioned, we have so many troubles caused by software elimination because the NIC, the network NIC, is not powerful enough. So would it pushes the innovation of the hardware? Maybe they can add more power to smart NIC, but I know they have their trouble too, like power control. But that perhaps indicates the importance to innovate the network adaptation. Okay, so I don't think I get too many time. So maybe I need to basically skip the second showcase. So the second showcase, I basically trying to describe what we are do to co-design across different runtime subsystems and optimize the performance in the hybrid MPI plus thread model that basically supports the QMCPACK application. Okay, so I will basically skip what we have done. Let's go to the takeaway. Okay, that's a quick summary. So basically, we actually got a lot of performance improvement by coordinating coexisting runtime subsystems. So for example, we have coordinated the MPI and OpenMP subsystems and to accelerate the communication in MPI. There are also other coordination we need to do, for example, between MPI and the GPU subsystem. And we may find that to efficiently utilize all of those libraries, we maybe need some different approach, like the low-level resource management, maybe at OS level. I know the OS innovation, they are doing such kind of research too. Maybe we can consider the more flexible and open interface of those runtime subsystems like MPI, like OpenMP, like a Pegas model, like the CUDA user space code to make the better interoperability so we can share information and provide more optimization for the system part. Okay. So the third example is still about multithreading, but it actually goes into the low level of the operating system libraries. So it tries, the core idea is that we see there are so many limitations caused by this process versus thread concept that are defined by the operating system long time ago. But for HPC community, we are hitting the extreme performance. So but if we can make a special customization for the process or thread definition, can we get a better performance? So this project, we tried that, and we designed a special thread implementation that's a HPC specific. It allows us to get rid of all these multi-threading plus MPI overhead we see. So this is a co-design of the runtime system and the low-level OS libraries. And I will skip this detailed picture so we can discuss at the discussing session if we are interested. And we are hitting up to 4 times improvement for the overall execution time of a snap application. So that's actually a lot. All right. So my last slide, my last showcase is about, it's not from our team, but from the collaborators at RIC in Japan. They actually even designed a new operating system for their upcoming Fugaku supercomputer. That will be the Japanese exascale supercomputer. So the idea is they change the design of the Linux system to make the computing part execute on very lightweight operating system and let the other servers be running on a separate normal Linux system. So that makes the applications running on the MC kernel part be much faster than that running on the normal Linux system. All right. So I still want to spend a minute to discuss what we are hitting the near future of HPC. So far, we all discussed is about the software stack. But as most of the community believes, the software and hardware full stack co-design will be the norm. So there are so many interesting discussions ongoing regarding the convergence of HPC and AI. For example, but actually we already have such project at Agam for the medicine processing and the cancer study. So the guess we are, and the assumption we are making here is that for the near future HPC systems, especially when we are trying to improve the HPC and AI applications, will we change the hardware system too? So for example, today we have so many AI inspired chips. So maybe in near future, we will combine them into the HPC system to address different AI tasks running on the supercomputers. Maybe we may design a specific hybrid chip even for the HPC. But the challenge here is how we will make the application, the programming model, and the runtime system designed for such extreme heterogeneous architecture. That will be an open question to everyone. Okay, so my last slide. Okay, so 1 minute late. HPC is powerful, but it brings so many complexity in software, hardware innovation, because we are trying to hit in the most complex problem in the world. We are trying to make address all those limitations in the current physical limitations. The system is going to be more complex, more heterogeneous. So we need to figure out a way, basically co-design approach to address the continued performance improvement delivered in software. One example is the ECP, Exascale Computing Project, funded by Department of Energy. There is actually a co-design centers. They combine the teams from application and the runtime systems to make the most important DOE applications co-designed and to get efficient performance on the exascale supercomputers. So such kind of approach will become the norm in the near future, exascale computing and beyond. So, okay, I think that's all I want to share for the talk. As we skipped so many details, I think we can discuss, and if you're interested, we can get back to the previous slides. Thank you.
Thank you, Min, for that excellent talk. And I got a lot out of it because I've kind of poked around in a bunch of those different applications. I'm the moderator, and I apologize for being a minute late. My name is Mary Hall from University of Utah.
Hi, Mary. Thank you for hosting this session.
Absolutely. And I don't see questions yet. Maybe somebody can tell me whether I'm missing them somewhere, but let me ask my own question.
Mm-hmm.
I was really interested in the NWChem data movement costs because they were really quite significant.
Yeah.
And you mentioned that one of the problems was that the data that you need to send is not contiguous in memory. So you're probably reaching around in different pages and things like, you know, at least different cache lines and maybe different pages. To
oh yeah, we can get back to that so we can have a better view of the problem perhaps. So I think this slide may explain the performance degradation we see, right?
Yes. And so I guess, so my question is, and this is related to my student Tuo and Zhao's research, he's actually looking at data layout.
Mm-hmm.
He's focusing on stencils, but it's kind of probably, this I think is because you have multi-dimensional tensors that you need to send, right?
Yeah.
And trying to lay things out in the order in which they need to be communicated, and then you know, having a data layout that is both compatible with the computation order and the communication order.
Mm-hmm.
And I wondered if such an optimization of the data layout might be useful here, in that is there some kind of pattern that you're going to send the same data to neighbor? Is there some static pattern across iterations, for example?
Okay, so perhaps this slide we can get a better idea about the data layout. So the data layout is not. I would think the layout of the data is considered of subpart of the 2D array. Of course, in multi-dimensional tensor, it can be 3D and 4D and so on. depends on the location, because each process will randomly pick the sub component from remote array, depends on their scheduled task. So the location of the sub block changes dynamically. They cannot be statically written. So I'm not very sure if that can continue this discussing about the data layout optimization you mentioned.
Yeah, I was just trying to I think the answer is potentially that you could organize the data in a different order, and then be able to communicate the parts that you need to communicate without, you know. So our idea is to put these blocks in contiguous memory, and then have some indirection that allows you to kind of organize the blocks. So
yeah, that's
anyway,
a cool idea.
If you could reduce, because the cost of that being in non-contiguous memory and kind of packing it is known to be high and to impact strong scaling. So
yeah.
So anyway, I'd like to follow up with you on that.
Yeah, sure. Yeah, I think that's a cool idea. And for NWChem, for the NWChem, because it's kind of limited by the random scheduling of the data access. But I would think that's a potential approach. We could get this problem optimized. As you can see, we are seeing the software emulation. That's really because the non-contiguous data movement is hard to be handled fully by the hardware of network. So if we can make it contiguous, yeah, that's perfect. And everything can be handled by hardware.
Yes, yes. Okay, we have a question from David Liu. David, would you like to ask your question? I'll give you a chance and then I'll ask it. Okay, the question is, are there opportunities for machine learning techniques to be used for HPC co-design, such as in communication pattern predication or beyond?
Oh yeah, definitely. And actually we are already doing that. That's a very interesting direction. And we actually have I have one ongoing work working with a PhD student in this direction. We are trying to use the machine learning techniques to understand how we can optimize the MPI collectives communication on different supercomputer systems. So if people have used the MPI collectives, they know that the collectives is really hard to get a performance portability because internally we design different algorithms, but those algorithms it's not really dynamically changed when we are changing onto different hardware. It's all by human, right? And we do this configuration and we do some maybe offline experiments and then we change the configuration statically, but that's not actually the ideal way. So we are trying to use the machine learning techniques to predict what will be the better algorithm we can use for MPI collectives. So that's something we are ongoing. Yeah, so that's an ongoing project. That's where we think it's promising.
And I have David says thank you.
You're welcome.
I have a somewhat related question, and it goes back to NWChem. I wonder if you've thought about, I mean, there's a lot of resources going to building deep learning systems that are also optimizing tensor computations, both on node and across nodes.
Yeah.
And so at least some aspects of that infrastructure would be in place in a deep learning system. And I'm curious if you have looked, if the developers of NWChem in general have looked at using, TensorFlow ecosystem with, or cuDNN / MKL DNN as part of the infrastructure for doing this.
I'm not aware of any public information regarding this aspect in NWChem team. But in general, yes, actually at our community, we have actually discussed the potential of tensor specialized runtime subsystem by utilizing some tensor-oriented hardware. Of course, the software system needs to be redesigned too. Yeah, we were not discussing whether we just use TensorFlow or the NVIDIA provided tools. We have discussing for that from the system software point of view. So to address general tensor-based computation in application layer. But yeah, I'm not aware of any activities from NWChem team. I know they are working hardly to adapt their applications on GPUs now.
Yes. Okay, so let's see. So I was curious about how CUDA was introduced into QMCPACK. I have looked at QMCPACK before, and it was an OpenMP. At the time, it was an OpenMP only application. And so, yeah. How do you have to write separate CUDA code? I mean, where does the CUDA code live in the application base? And how do you decide you're going to use that versus use OpenMP and threading?
Okay, that's actually a good question to me. Actually, I don't know where is the CUDA code in their QMC software stack because I think that's something really they added recently, and with only limited functionalities, I think it's not enabled by default. So that's basically, I think that will be something they, because so QMCPACK team is very close to, they're also at Agam. So what I heard from them is that because of the Aurora supercomputers, that's their goal to utilize GPU accelerator in their code. But I think there will be some challenges they are still addressing now. One example would be how they would put such large replicated the ensemble tables onto GPU memory system, because we already hit the problem on the CPU memory system. So that's something they are addressing now. That's why it has only very limited support. Yeah, but I'm not aware of where the code actually exists in the pack because I haven't used the CUDA part yet.
Sure. I guess I'm just kind of looking at the big picture question of how do you mix all of this stuff in a single application so that it's performance portable? It's certainly not single source performance portable, you know, that you have to explicitly have CUDA code.
Yeah, it's not that. There are some high-level frameworks like Cocos. They are trying to make the code more like single source code portable and with performance portability. But that's not covered by the examples in my talk today. But that's basically something definitely ongoing in the community.
That's right. That's right. See. So when we run out of technical questions, we can have an Ask Me Anything session. So what was your training that prepared you to do this kind of work? And what would you tell, you know, an educator like me that students need to learn in graduate school in order to be prepared to do this kind of work?
Oh, okay. Yeah, that's a very interesting question. Let me think. So to motivate me to continue work on this direction, it's actually really because I'm interested in the data movement challenges and the problems while I was a master student. So and at that time, I just started my parallel programming, and I found there are so many interesting themes where are coordinating between multiple processes, multiple threads. So that needed me to continue working into this direction and go very deep of this HPC, so many HPC software stack, and working at the low-level communication runtime and looking at the different layer of the full stack in both software and hardware. So that's basically why I'm working for this direction, and I'm very happy to doing that. For the suggestion, maybe a little bit advice to the young graduate students, yeah, I think it will be good to have experiences involved in several projects of those high performance computing application team or at the system team. Maybe just deal with a very small problem at the very beginning, but they will get experiences and some level of knowledge about how HPC works, because I think from the outsider of HPC, it's not really to understand what's happening inside HPC. I cannot even explain this to my parents, for example. So I think the students, it will be very beneficial for them if you can in touch with a project at a very early stage, deal with a small problem, and then they can starting from that point and expand their knowledge across into other different directions in the HPC problems.
Well, that's good. A good suggestion, because it is the case that you run into some of these things that conceptually wouldn't be a big deal, and they turn out to kill your performance. I mean, kind of along the lines of your whole talk, right? That things seem fine, and then you actually bump into some bottleneck in the system and then you learn all sorts of stuff from that experience, and that's really kind of learning from doing.
Yeah, yeah. These are so many funny things happening in this the stack research, HPC research. Many of the bottlenecks from like I think one experiences we have learned is that even maybe sometimes we see a small bottleneck and maybe just a mistake or something we think it may be trade-off in the software design, but that may actually become a huge performance bottleneck when we are getting into a slightly different computational paradigm. Maybe we change the layout of the data, for example, and maybe we change the, maybe some applications that are just irregular, so they randomly jump into that bottleneck sometimes. Yeah. But so I think that's something we could definitely get from small problems, small projects, and explore more and deeper and get a large impact eventually.
Great. That's a really good suggestion. There's a lot of talk right now about, given how these hardware architectures are diverging in so many different ways, that the programming of them is going to be very difficult, and so there's a big challenge in training the workforce to make them prepared for all this architectural diversity. And when you get down to node level performance, how do you generate the code? So that's kind of was getting at the CUDA versus OpenMP question of the code that you need to write is very different.
Yeah.
And so there's a big interest in workforce development. I've been really thinking about revamping my graduate class to try to prepare people for that. So it's interesting. I mean, probably getting a piece of an application makes a lot of sense.
Yeah, I can see there is actually a great need for that, because we are waiting for like a fresh blood join the community, and I can even see so many trouble, so many time we have to spend to educate ourselves to be able to work on a new different hardware system. I can expect how complicated that will be to educate the new developers or new researchers. And yes, I think definitely getting not only the, so because I think in HPC, we were working for benchmarks for a long time, but that's not really, sometimes really getting like touch with the applications with a bigger system, but of course from a relatively small point of the system, that will be greatly helpful to understand what's the full scale of the supercomputing.
Yes. Do we have some other questions from the audience? Maybe you can just raise your hand and ask. And now we're in the Ask Me Anything, although I'll come up with some other technical questions in a minute.
Mm-hmm.
So, so let me try something else. So as you're preparing for the ECP architectures,
Mm-hmm.
how do you need to modify these applications? Are there things you know you need to do to modify these applications further?
Yeah, okay, that's a very challenging question to me. Yeah, I could not actually, maybe I'm not the right person to answer for that because I'm trying to resolve everything. Most of the work will be in the runtime part, so in the low-level runtime part, where we are trying to abstract and we're trying to minimize, compress the additional information we need from the application. So what we do is to redesign the software system or redesign the runtime interface or extend them, and to get that additional information reached into the runtime part, and so on, we can optimize the performance and get a good performance on it. From the application point of view, I know there are teams, they are actually doing a large proportion of code rewriting for the in the ECP project. One thing I will observe is that they investigated whether they basically want to do some minor extension, for example, just change some computational expensive portion by replacing with a CUDA code running on GPUs. Or they are also investigating approach that maybe they want to fully rewrite the entire software, at least the most important computational kernels, by leveraging some performance portable framework or languages, like they do the domain specific languages. They have their the Cocos, Raja, those performance portable frameworks. So they are investigation whether it's worth to fully write an application by using a completely different communication programming interface. Yeah, and so I probably I'm not really answer your question on this direction, but yeah, I'm just sharing what I have observed through the big ECP project.
Yeah, it's interesting to imagine how people are going to deal with these new instruction sets and programming interfaces, and you know, at the runtime level, it's really about scheduling and data movement. But
right,
all of those things are going to be different on these new architectures. And
yeah, exactly. We are working very hard to make the figure that one example is we're doing very hard to really optimize data movement when both CPU, GPU are being used, and we are trying to make it scale. That's really challenging for the ECP project. And I think if we can move a bit forward to the next generation, perhaps post the exascale, it may not be only GPU, it may be something else.
right.
That may even make the situation more complex.
That's right. And I don't have any other questions from the audience. I always have lots of my own questions. The programming stack that you have shown for these things, so some of them, so QMCPACK is using standard things, right? It's using OpenMP and MPI and CUDA. But in NWChem, a lot of things are built, you know, are things that have been built specifically for NWChem. Well, I'm trying to remember exactly what you showed. You showed global.
Oh yeah,
maybe you can
have we can have the slides back here. Yeah, they're designed. They're basically better than most of their runtime system.
So so it's built on top of. So there's an application package and it's built on top of global arrays. And because of that, then you get the portability to different kinds of, you know, MPI implementations and different network capabilities. to what extent do these things that are either application specific or, global arrays is not application specific, but I'm guessing that NWChem is one of the big users of global arrays. Is that correct? Yeah. So how does that impact optimizing the code, the fact that there are these, the software infrastructure is not like a super standard thing like MPI and OpenMP, but something that is more designed for particular kinds of application domain.
Yeah, I think this will be a good, global arrays will be a good example of the high-level library that are specifically designed for a subset of applications. NWChem is the most widely used, one most important application at the for the global arrays team. I do know there are some other applications, but they are not as famous as NWChem. But NWChem, from my understanding, global arrays basically trying to give relatively generic support for the tensor-oriented applications. So you can see their principle is to abstract the huge array, which would potentially be used to hold large tensor data and across node, and so they can let the application developers to concentrate on the algorithm rather than caring about the data locality and so on. So that definitely would help a set of applications. Yeah, and from the developer point of view, it gives us relatively simpler interface to learn. For example, if I'm an MPI developer, I'm trying to understand how I can use MPI code to implement the global arrays. That's much simpler than understanding the full code of NWChem itself.
Yes.
Yeah, so that's I think it's a trade-off. It gives us benefit. It gives us benefits for the relatively simple development and code maintenance and reuse. So that's basically, I think there's a great trade-off happening there. And I can see the global arrays team, they are also trying to rewrite and optimize their code for exascale computing. They are adding more heterogeneous support in global arrays, for example.
I wonder, so the optimizations you were doing, they were at the NWChem layer, right?
I think actually most of my effort are for the runtime part. So basically, we have the
Where does that
layer, yeah, in the runtime part, not in the application code itself. But we do need a lot of information from, not a lot of information, but some key information from the application layer. So that's why we need those applications information to be exposed to the runtime part. Then we can do a lot of work to utilize those information, for example.
Yeah, I was just trying to get at where you might invest some resources, invest time in doing the optimizations that could then be translated to someone else's, someone else might benefit from the same thing. A different application might benefit from the same thing. So I was a little confused as to where the optimizations were occurring.
Oh yeah.
If they're happening at the runtime layer, then in fact, you could potentially use the same optimization. Is that correct?
Yeah, that's one reason we did it in runtime, because we consider we want to support different applications by using the same approach. Yeah, but I think one interesting aspect we actually I observed through your question is that so it's not really something like we get some information from application and then we get it to work at the runtime. We actually need to design the program interface for that, so that information exchange effort can be portably and used in different application development. That will, that's actually a challenge task too. to standardize those programming model and interface to support co-design, cross-application, and runtime. That's another challenge.
That sounds like an interesting research opportunity, actually. So.
Yeah, exactly.
Yeah, I'm trying to think of something else. It's not coming to me. Want to encourage the audience once again, and then what are some things that you want, assuming we have some people that are entering the field in the audience, what are some things that you would like to tell them about the future of working in HPC? Is it a dead-end field, or is there something happening? What's happening? I know it's not, so that's why I'm asking you.
Oh, okay. Yeah.
Where's the future? What are the opportunities? Where is the field going?
Yeah, that's actually a big question. And let me try to provide a little bit insight from myself. HPC community, as we know, it's not really a big community. It's so focused, and we are trying to actually engage the interest from a broader computer science community. For example, we're trying to figure out how we can use HPC power to solve more problems that are not in scientific domains, like and there are many industries, like for example, Facebook, like Google, they are also learning how they can use special HPC supercomputers to address their computing questions that cannot be done on cloud systems. So that's actually definitely involves, like encourages more researcher and developer join the HPC community. And from another direction, because everyone is so interested in the AI, now they can be AI for HPC or HPC for AI. There are so many ongoing discussion for that. That definitely drives the next innovation or development of the HPC systems. So as one example, we have already observed that the exascale supercomputers, they are already designed for such heterogeneous requirements from both simulation and deep learning, for example. So there are also ongoing discussing at small worker groups about what if we have more diverse computing requirements on the that we need to address on the supercomputers. So for example, we all know that the deep learning training is very expensive, so we can run it on supercomputers. But if we want to minimize the data movement, we may want to do some inferences on supercomputers too. And then when the inferences task becomes dense, we will hit performance limitation there. So we may need to have new architecture embedded into the traditional HPC system to address such requirement. So that's one direction we are considering that will be a near future of the HPC, specifically address AI for HPC for AI. Yeah.
Mm-hmm. Good. Yes, I think that one thing that that people are really interested in is how you might speed up simulation, by learning some things and computing fewer iterations of the simulation because you're accelerating it somehow with learning. And I think that's another sort of interesting direction. And the thing you mentioned in your talk about using deep learning hardware in the middle of something like Candle, where
Oh, yeah.
where learning is part of the application. I mean, that's what did you just call it? HPC for AI? I mean, isn't that's kind of what, it's a mix, right? Because
Yeah, it's a mix, yeah. Yeah, so for this project, we already, I'm not directly involved in the Kernel project, but we got a lot of information as it's a project led by Agam. And so in this project, it's already, I think it's already about 2-year effort. And we have seen there are the requirements from the science side. They really need to run simulation, deep learning together. And so they use simulation to generate data. They do and then they will use that data to run the deep learning training, and then they need to predict what will be the, for example, the research for a patient for the medicine part. So that kind of mixture of simulation, training, and inferences. That's a good, very good project to motivate that our future HPC system will be more complex.
Yes, yes. Many more things to worry about, even more complex hardware to worry about.
Oh yeah, yeah. We are all talking about the performance per watt that basically limit us to use those generic processing cores. We have to make all cores specialized. Then eventually we have many different kind of CPU processing cores on a single system.
That's right, and you know, it's more efficient to build these coarse grain hardware, you know, resources, and then use them, because you don't, you know, there's lots of scheduling and data movement optimizations that you get out of using custom hardware. But unfortunately, then you have to figure out how your application can be reconfigured to be able to use the special purpose hardware. And you know, I look at it from the compiler standpoint, and there's a challenge of sort of finding those opportunities to use, you know, like taking an application and converting it to something that matches the constraints of the hardware. So I'm very fortunate to be working in compilers while those architects are doing all these crazy things, because it gives us, you know, lifetime of employment with all the interesting changes that are happening in hardware.
Oh yeah. Yeah, compiler will take a very important role here to make the performance being portable on different chips. Yeah, I can see that. And I know the application teams, they are trying to, I don't think they are trying to actually replace the entire application code to run it on a specific core. They're basically doing at the kernel level.
Yeah.
So yeah, so the challenge will not be that unresolvable, but definitely we need to do a lot of work to make it more flexible for long term, and in compiler, in runtime system, in program interface, and operating system as well.
Yeah, that's right. Okay, so we're coming to the end of this session, and as I understand it, people can go to the Meet the Speaker session, you know, following this, and also there's a way to put offline questions if you want to ask questions after the talk. And so I would just like to thank Min for an excellent talk, and thank the audience for sticking with us. And I guess that concludes.
Yeah,
thank you.
Thank you, Mary, and thank you, everyone.